Hello everyone, today we are going to talk about Z function. Today, we'll cover three key topics to explain the concepts in this lecture. First, we will review the power density equation of the superconductor composite that we have studied previously. Next, we'll examine how the Z function is calculated in a constant current mode under adiabatic conditions. Lastly, we will briefly explore how the calculated parameters using the Z function are applied in magnet design. This page contains parameters commonly used in Chapter 5. In a superconducting composite, the power density equation can be constructed using 5 key elements: storage, conduction, Joule heating, disturbance, and cooling. In adiabatic conditions, we ignore conduction, disturbance, and cooling in the power density equation. Next, we will make a few assumptions in the constant current mode. First, we assume that even in a quench situation, the current supplied from the source remains constant. Second, we assume that when a quench occurs, all the current flows only through the matrix region. Additionally, for simplicity in calculations, it is assumed that the specific heat of all materials within the superconducting wire is similar. Under these assumptions, the power density equation, which now only includes storage and Joule heating terms, can be simplified as follows. The parameters shown here relate to the matrix ratio, which can be understood by reviewing Chapter 2.1.2. Ultimately, this leads to the derivation of the Z function. The Z function, which can be calculated using enthalpy, is a useful tool in our analysis, though its detailed calculation will be omitted in this video. Next, we present the Z function values for several materials used in the matrix at different temperatures. The Z function is used by calculating the difference between the Z function values at the initial and final temperatures for the material in question. This difference helps us determine the time it takes for the material's temperature to rise from the initial to the final temperature when the matrix current density is flowing. In this lecture, we refer to this time as the temperature rising time. Understanding the Z function values and their implications for temperature rising time is crucial for predicting and managing the thermal behavior of materials under operational conditions. There is a simple table calculated using the Z function. This table compares the temperature rising time, denoted as Tmax, with the normal zone propagation time in the transverse direction, as covered in the previous chapter 5.2.2. The values are calculated for magnets composed of various superconducting materials. On the left side of the table, for two types of materials, the normal zone propagation time is shorter than the temperature rising time. This implies that even if a local quench occurs in these magnets, the normal zone propagates more rapidly than the magnet heats up locally. As a result, the rapid propagation of the normal zone allows engineers to detect and address the issue before significant localized heating occurs. However, on the right side, for the other two types, the temperature rising time is shorter than the normal zone propagation time. In these cases, even if a quench occurs locally, the slow propagation of the normal zone means that the local area may sustain damage due to burning before the engineer can detect and address the issue. This use of the Z function enables us to infer the protective capabilities of the magnet and assess potential risks associated with different materials used in its construction. Today, we explained how to use the power density equation to determine the Z function in an adiabatic situation. We also explored how the Z function can be used to calculate the temperature rising time from the initial to the final temperature. Additionally, we provided a simple example comparing the temperature rising time with the normal zone propagation, NZP, time to highlight the differences in terms of protection. This comparison helped us understand how these calculations can provide engineers with valuable information regarding the protection of the magnet.